Okay, so today we will discuss cubic theory. So this is the class group of models that we are going to discuss for our course. So I will provide a short intro, and then we will discuss several queuing models which are simple, and at the same time they also have some real life applications. Yeah. Okay, so maybe you can imagine a point in your life when you have to line up or to join a queue to avail of a certain service. So maybe you have some experience with going to uh, government agencies, like for example, before you have to maybe get your birth certificate. Okay, then you have to go to the PSA office. You are going to get a priority number, and then you wait for your turn. So that is actually an example of queuing. Another example is when you go to the department store or the grocery, and then after you get your uh, items, then you go to the cashier to pay. But sometimes the cashier or the cashiers are occupied, so they are still currently servicing one customer. Then for that, you also have to wait. Okay, so that's also example of queuing. Aside from that, there's also some uh, circumstances or situations wherein you are effectively joining. You can still consider that as a queue. So an example is when you want to you submit a document to the or you are processing some documents, or for example you are processing for your online classes. So you have course requirements, right? So you have a lot of courses, and each of these courses require you to submit some requirements. So sometimes maybe you try to schedule which time you do the particular requirements, and so the other requirements sort of wait before you do them. So that's also an example of a queue. And there's also like when you have experience riding an airplane, right? So these airplanes also queue uh, in the field before they take off. So they wait for their turn to take off, or they also wait for their um, turn to land. So these airplanes are also on a queue. Yeah? And maybe as a last example, so when you are on a traffic or you are in a traffic light, or you are on the road, okay, you are commuting, going to work. So sometimes the traffic sign shows red, so you have to stop. Okay, and of course not only you but also those other cars or other jeepneys on that side of the road. So you have to wait, right? But sometimes this wait can take very long. So that's one of our problems before, because the traffic is not moving, right? So that way you are also waiting. So there are many instances where there is an element of waiting. Okay? And these models that we are going to discuss now may be used to model, okay, the efficiency of those systems that involve waiting. Okay, so we will have this Kendall notation. So we usually denote a model using four numbers, but usually tatlo lang yan sila. Okay, we just add fourth one to indicate if our system has a capacity, which is actually in most practical settings, they have capacity because, for example, sa mga grocery, meron naman talaga yung capacity, but we just assume for the sake of simplicity, or maybe we don't really need that particular restriction, that capacity, then we can just assume that we have an infinite capacity. So we often omit this uh, part of the model. Okay? So we have basically three. First is the arrival process, service process, and the number of service. So in a queuing system, you have there the queue, okay? You have there the service, and people enter the queue from a certain population. The process by which they enter the queue, the system, the queuing system, is what is described by the arrival process. Okay? And of course, when you enter the system, if someone is already being served, uh, someone is already being served at the moment, then you have to wait in the queue. But if the service or server is empty or unoccupied or not currently serving a customer, then you go directly to the server. Okay, and the amount of time it takes, or the amount or the process by which this server um, accepts customers and releases customer is usually described by a service process. And the last parameter is the number of servers in the system. So it can have many servers. It can have one, at least one. Okay? Hindi pwede na zero kasi hindi na, walang customer na. So pasok lang ng pasok mga customer. Wala nang lalabas. So the tendency is it will overwhelm the system. Okay, so we should have a number of servers with at least one, and that's the process how we um, release a customer. Okay, or how we release a specific item, maybe in a production line. Okay, so the symbol that we use is arrival, service, and number of server. And usually we define the arrival and service process based on the distribution of the time. Okay, so for the arrival, the time between two successive arrival, and for the service is the length of time of service. Okay, and for the arrival process, usually we assume that it is memoryless or Markovian. We have already discussed this. We have some implications. For example, if it is a Poisson process, then there's an implication on the inter-arrival time. So the inter-arrival time is the time between two successive arrivals. Okay, but we can also have, aside from memoryless or Markovian, we can also have an Erlang K. Okay? So as you have learned, Erlang K is it's just the summation of inter-arrival time of exponential distributions. Okay, so if you want to sum k exponential distributions that are independent but identically distributed, um, uh, exponential, then that is Erlang. Okay, and lastly, we can also have deterministic. So those are the top three. But if you want to also incorporate other distributions in the inter-arrival time or service time, then you may use a general inter-arrival times. So it's a bit general because it's not restricted to Erlang or exponential families. But we still assume that it is independent and identically distributed. And of course, for the general service times, is we denote it by G. So if our notation shows MM1, means that the arrival process is memoryless or Markovian. The service process or the time, service times are also exponentially distributed or Markovian, and we have number of service. We will discuss several of these models. Okay, so when we say memoryless, so that's where the M symbol comes from. It can be memoryless or Markovian. They are sort of the same. So memoryless means that arrival process that it indicates that this is Poisson. Okay, so it means that for any period of time or duration of time, the number of observations in that time period is described by a Poisson distribution. Okay, and if that is the case, then we have a Poisson process. And one of the implications of a Poisson process is that the time between arrival is exponential. Okay, it's an exponential distribution. Same thing, if we assume that we have an exponential service time, it also means that the service time is exponential. So that's just the implication. Okay? Then we have here a very important formula called Little's formula. Well, it's not called Little because it is small. It's called Little because a person named Little first proved this formula. So, apelyido niya ay Little. Kaya tinawag natin siyang Little's queuing formula. And this formula is ano yan siya, encompassing. It means that it applies to any queuing system. Provided that they have a steady state distribution, it means that the number of people in the queuing system is achieves a steady state distribution. Remember that the number of people in the system is described by a Markov, right? If we assume a memoryless or Markovian. So it can be 1, it can be 2, it can be 3. And what's the probability that it's 1 going from at any time in the system? Okay? Then you can specify the probability that there are 0 people, there are 1, there are 2, and they sort of reach what we call a steady state distribution. So what this formula is very useful because it relates 3 important characteristics or property of the queuing system. The first is average number in the queuing system, so L. So L here represents the average number. So how many people on the average you can find in the queuing system. Okay? So maybe you can apply this sa grocery store. Let's say sa SM supermarket or maybe not in SM but in Save More. Okay, so how many people you can expect in the queuing system at any given time on the average? So when we say queuing system, it only involves the people in the queue plus the people currently being served. Okay, so that's hindi nakasali yung mga nagpili pa ng mga grocery items. Hindi yan sila kasali muna. Okay? So we are only concerned with average number the queuing system. So that is the L. And we have also this lambda, which is the average arrival rate. So what is the average arrival rate? Okay, how many times per minute, per hour? Okay, we expect arrival. So that's the arrival rate. And W, unlike L, which refers to a number, W is actually time. So when we say time, we talk about duration. So average time in system per customer. So this answers the question, okay, if I'm going to save more, how much time I'm going to spend in the queuing system? So how much time I'm going to pay, how much I'm going to spend, I wait in the queue, and I'm being served. So you total the time, that is the time, okay, in the system. Okay, so maybe during afternoon there's a lot of you spend a lot of time in the queuing system, but maybe in the morning you spend less time. So that is the average time in system per customer. Okay, so you just need to remember this is a number, this is a duration, and this is a rate. And these 3 quantities can be described by the average number is equal to the average arrival rate times the average time in system per customer. Okay? So intuitively, how can we sort of describe this intuitively? It seems obvious, right? Because you have here the average time in the system, and this describes how many people are arriving, because this is the rate, right? And that is actually the average number in the queuing system. Okay, so you can also analyze this in a perform dimension analysis. If this is time, and if you have rate as the people per time, cancels the time, right? So we have time, so number of people divided by time, uh, um, number divided by time because it's a rate, and this is time, so it cancels, right? So parang system is looks like this, and so you have number over time. This time is duration times the time, because this is the average time. So if you multiply, it will cancel, and you will end up with number that is okay. So that is the queuing. But let's also give a very intuitive explanation of the Little's queuing formula. Okay, so you can imagine that you join a queue, okay, and you spend W minutes before you have been served and leave. Okay, so that's the time you've been served and the time that you leave after, right? So during those W minutes, yeah, customers have been arriving and joining the queue behind you at the average of lambda per minute. So remember that you have a customer arriving, right? You're arriving, and then you join the queue behind you at an average rate of lambda per minute. Or this is already quantity, right? So lambda per minute. That's when you are ready to leave, you should expect to see lambda W, right? Customers remaining in the system behind you. Because the idea is you have a lambda, the rate of arrival. No, remember, it's a rate, the average arrival rate. And you have the time in system per customer, average time in system per customer. So once you enter, someone someone is being served at that time, and then you enter the queue, and then if this someone has been finished um, uh, receiving service, then behind you, if this is you, you would expect that there are also like lambda, on the average lambda per minute. Therefore, when you're ready to leave, you expect lambda customers remaining in the system behind you. So this is not only in the queue, but also customers that are being served. Okay, so that's the short explanation or intuitive argument for the Little's queuing formula. Okay, so let's obtain some theoretical results about different queuing models. Okay? If we assume that the inter-arrival and the service times are memoryless, so it means that they have exponential. The inter-arrival time and the service time are all exponential. We will deal with, if there are one server, we will deal with if there are more than one server. No, we can deal with one server, but we have a finite capacity. Okay, or we can also deal with one server. We have finite capacity, okay, and finite population, and a case in which service time is not memoryless, but you have only one server. You will analyze later a very interesting problem. You notice that if you go to save more, you can actually line up where there is a cashier, right? So if you are carrying a push cart, you can line up directly to the cashier. But in the case of if you're carrying a basket, sometimes some grocery stores require you to line up on the same line, right? And then whichever is available cashier, then you go to the next available. So which one is more efficient? Do you form different separate line for each cashier, or you just form one long line and then you go to the next available cashier? We will analyze that because that will really help you design your queuing system. Okay, let's deal with MM1, exponential, Markovian, and we have a one server. Okay, for the inter-arrival times and service times, both have exponential distributions. Okay, so you have lambda and usually denoted by mu. Pag service time mu, pag service rate mu, and arrival rate is lambda. So that is the customers arrive at the rate of lambda and are served at the rate of mu per unit. So this usually means like how many would you expect at a certain time period that will arrive? So within 30 minutes, how many customers you're going to expect? Or within an hour, how many customers are being served? So that's those value. That's those instances what these values represent. Okay, so it is assumed that the queue has infinite capacity. It means that walang limit ko, walang limit. Pwede kahit na 1 million nandoon, pwede walang limit. So make assumption. Basta wala lang siyang restriction. It means that if someone goes there, he will not be declined because puno na ang queues. Yan ang ibig sabihin yan. Okay? Kasi merong iba kasi that you come and then they say, oh, hindi na pwede kasi puno na kami. Merong ganyan kasi na case. Pero ito, we assume that that will not happen. Okay? So everyone who wants to enter the queue the queuing system can enter the queuing system. Okay? And then we assume, of course, that the service rate is higher or larger than the arrival rate. It makes sense kasi kung mas mataas ang arrival rate sa service rate, the tendency is ma-blow up ang system. Managahan na ang system na to. Inefficient na siya, kumbaga. Yeah? So it means that yung length ng ating queue, hindi naman siya haba na mahaba. Okay? So in this case, it is possible to derive the probability distribution of the number of customers in the queuing system. So kailangan natin i-derive yung number of people or customers in the queuing system. Specifically, you want to derive the steady state distribution. Yeah? Okay, so suppose that this is the steady state distribution of customers and the MM1 queuing system. Ito is pi sub-0. It means the probability, no? Na walang customer sa queuing system. Remember, it's a queuing system, hindi yung queue. Hindi yung queue. Kasi yung queue, ang queue, yun yung line. No? Ang queuing system, the line plus yung siniserve. Okay? So lambda pi 0, pi 1, and pi 2. So it can be until infinity because we assume that walang limit yung ating queuing system. Okay? So of the number of customers in the system, that is 1 plus the number in the queue. So pag 0, meaning wala sa queue, wala nag-serve. Pag 1, usually it means that walang tao sa queue pero merong siniserve. Pag 2, meaning mayroong isang tao sa queue, merong isa currently being served. Parang gano'n ibig sabihin. Equivalently, pi I is a probability that every customer will find I customers already in the queuing systems. So how do we denote the probability? Very simple, you just have to 1 minus lambda over mu times lambda divided by mu raised to I. Okay, so that's the probability. Okay, because this is This is if we assume no that lambda is less than mu, so this will always be less than 1, right? And we can take that as a probability. Okay? So that's the probability. Now, using this probability distribution, we can then derive the average number of customers. So using just an expectation. So how do we compute expectation? So just the value times the probability of that value. Okay, so you have this I times probability that there are I people system. You sum it up for all values of I, then you get this formula. And then since you know that lambda over mu is less than 1, you can apply the geometric, correct? Okay. Yes, exactly. So you have L equals lambda over mu divided by 1 minus lambda over mu, or you can denote this as rho. And actually rho here, the symbol rho is the utilization factor actually. Okay, that is should be less than 1 because we assume that mu is greater than lambda. Okay? So for the MMQI system, this formula implies that W equals L over lambda or P lambda or 1 minus mu minus lambda. Yeah, that's very easy. And it's very intuitive, right? So the number of people in the system is just equal the average number, the average length of time that you spend in the queue is equal to 1 minus mu minus lambda, or service time minus the arrival, the service rate minus the arrival rate. So that is the expected length of time you would spend in the queuing system. Okay, so you have W sub q, and this one is already denotes the time you spend in the queue. Okay, and the number of people in the queue. Pag mayroong queue dyan, it means that you are only talking about the queue. So yung line ba, minus the service, the people currently being served. Okay, so this is also very important because you might ask, okay, how long ba tayo maghintay bago tayo ma-serve? Yan yung mga question. Kung mataas yan, meaning mapagod yung mga tao. Okay? Lalo na yung mga gurang. Ang mga gurang kasi, di ba, ayaw nilang matayo. Ayaw nilang tumayo. Matagal. Di ba, meron na sila mga rayuma. Tama? So that's why they give you nga kasi ibang bansa, no, kung mag-line kayo, meron silang mga meron silang mga indication na from this point, you have to wait like 5 minutes. Parang ganon yun. Just to tell you how long are you going to expect. No? Tapos mag-move ka na naman, and then pag malapit ka na, meron din nakalagay doon. At this time, you will wait for 2 minutes. Parang ganon. Sana yun ang gawin natin dito para hindi natin ma-expect na matagal. Lalo na dyan sa mga government agencies natin, matagal sila masyado. Lalo na yung BIR. Gabi tagal dyan. Kakapal na mga mukha pa ng mga tao dyan. Diba? They're wasting our time. So, dapat natin sila, puntahan natin sila, and we'll tell them how to improve their system, queuing system. Okay? How long are you going to wait? And how many people, so that is the L sub Q, you're going to, how many people you would expect to be in that queue. Okay. Bakit importante ito, itong LQ? Because sometimes, meron kasi mga cases na pag mahaba masyado ang linya, ma-discourage yung tao na mag-line. Okay? So, di ba, pag sabihin, grabe ang linya, ayaw ko na balik na lang ako. Parang gano'n na mangyari. Ang tawag natin dyan is balking ang tawag natin dyan. So if someone decided not to join to enter the queuing system because the queue is very long, then that behavior is what we call balking. Okay? Meron din actually na mga tao na nagsisingit. Actually, pwede nating ma-model yan. Ang tawag naman sa mga tao na nagsisingit sa mga line is infiltration or pwede siya mag-infiltrate. Okay? So yan yung mga nagsisingit. Siguro yung mga fixer yan, singit-singit sila sa line. Diba? So pwede nating i-model yan. How many fixer ba ang kailangan natin? How many customers ba ang i-accommodate natin through fixer? Yeah? So that is actually infiltrating or infiltration. Yeah? Marami yan. You can think about many scenarios that we can model dito sa queuing system. So those are just formulas. So very easy because you can automatically use this formula and they are just expressed in terms of the rates, the arrival and the service rate. Okay, so let's have an example. So an average of 24 trucks per 8-hour day arrive to be unloaded or loaded, okay? Which requires an average of 15 minutes. So mayroong mga truck na dumadating, because it takes them on the average 15 minutes para i-unload yung dala nila. Okay? And the loading dock can handle only a single truck at a time. So meaning, isang server lang yan siya. Okay? So assume that the arrival process is Poisson and that the service times are exponential. Of course, in real life, you have to check whether these assumptions are true or whether this assumption holds in your system. So kung arrival process natin ay Poisson at ang service time natin, ang service time natin is exponentially distributed, it means that we can use that, in this example, MM1. So ano yung mga kailangan natin i-compute na interesting that we can describe dito sa queuing system? The number of people in the system, the average time you will spend in the system, the average time you will spend in the queue, and the average time you will wait in the queue. Okay? So, to compute for the arrival rate, since you have here 24 trucks per 8 hours, so you just divide this. Okay, so 24 divided by 8, so that is 3 per hour, and which require 15 minutes. So how many ma-serve mo in 15 minutes? Kung 15 minutes ang it takes to unload or load a truck, how many? In an hour, how many minutes ba? 60. So therefore, kung 15 minutes ang isang truck para ma-unload or ma-load, therefore you have how many trucks ang ma-serve mo siya in 60 minutes or in 1 hour? That is 4 per hour. Good, very good. Okay, and then utilization is just the ratio of the service rate and the arrival rate over the service rate. So in this case is 0.75. So alam natin na hindi maging ma-overwhelm ang system kasi nga the server or the service rate is higher than the arrival rate. And what is the average number of truck in the system? So this is the truck in the line and truck being currently being served is just 1, right? So we have 3, good. So yan lang, ratio, apply the formula. And the average time in system per truck is W equals L over lambda equals 3 over 3 or 1. So kung ikaw yung parang driver ng truck ngayon, so when you arrive, the average number of trucks in the system, you would expect that there are 3. Okay? And average time naman kung papasok ka system is 1 hour. Okay, so pwede mo na yung i-incorporate doon sa sa iyong time or schedule na it takes 1 hour pala for this. And it is for the steady state behavior. Okay, the average time in queue, simple lang, 1 minus the W minus 1 over this is the service time, right? Or 0.75 hours, right? Because it takes how many? 15, diba? So 0.25 hours. Okay, good. And the average length in the queue 3 times 0.75 or 2 point. So when you come, you expect around 2 car trucks. Now, if we have a model that has C servers, so it means that it can have 2 or more, right? And the inter-arrival and the service time is still memoryless or exponential. Then of course the mean would be 1 over mu lambda and 1 over mu. That's just the mean number of customers, or the uh, distribution, or the mean time. Okay, what's the mean time between? So that's 1 over mu, or 1 over lambda, and the mean time being served is 1 over mu and 1 over okay. And we have the number of server is C. Okay, so the capacity of queuing system is still infinite kasi wala naman siyang ika-void. Okay, if the arrival rate is less than the combined rate of all the servers, so remember that we have now C servers. So each one has mu. Okay, mu ang kanilang service rate. So therefore, we just multiply, right? Or add, or add them. But here we can just, since pare-pareha naman ang kanilang service rate, so C times U lang. Okay? At which the servers can work. Then the system will have a steady state distribution given by, so this is how you compute it. Okay? So lambda 0, lambda j. And this is just actually manipulating in terms of C mu. Okay? Okay? And then the utilization, yan yung tatawag na utilization of the server is lambda divided by CU. That is very obvious naman yan kasi kanina wala lang C. Wala lang tayong C times U, but U lang. Okay? And then the probability that all servers are busy is, okay, lambda j greater than or equal to Z is C times rho times raised to C divided by C factorial over 1 minus rho times pi sub 0. This then is a probability that an arriving customer will be required to wait for service. So that's the probability that when you enter, you have to wait. Okay, so what's the average length of queue? Okay, ito lang yung formula. You can read about this sa book din naman. Okay, and then average length of queue, this one. So once L is computed there, we can compute this in Little's formula. The average waiting time in the queue, because LQ over lambda is equal to the average time in the system is the average time in the queue plus the 1 over mu, or the service time, and L is equal to lambda W. Okay. So let's try to analyze yung sinabi kong example kanina. If you have like, let us say 2 servers, okay? Saan ba ang mas efficient? You form separate lines on the 2 server, or 1 line lang siya, and then the person or the customer will go to the available server. May imagine niya yan. Isang linya lang, tapos kung merong bakante doon sa server, doon ka pupunta. Or mag-form ba tayo ng line in front of each server? So yan yung question. Okay, yan yung tinatawag natin pooled or separate servers. Okay, so kung arrival rate natin dito is 4 per hour, okay, kanina 4 per hour. And then dito naman is 8 per hour kasi nga isa lang siya, isa lang line. And then mu is of course the same, di yan siya nagbabago, 5 per hour kasi nga they're still independent pa rin naman. They don't help each other, dependent lang, okay? So kung separate, we can analyze this just like a 2 MM1 queues, okay? Separate. And the average waiting time is lambda over mu minus lambda is equal to 4 by R, 5 over 5 minus 4, 0.8 hour. So that's the average time you have to wait in the queue, 0.8 hours or 40 minutes. And if you're going to look at the probability or the steady state distribution, ito yung probability na 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on and so forth. And then, kung single MM2Q naman, so yung pooled, so arrival rate mo is 8, pero service rate mo pa rin is the same. Okay. Rather than maintaining a separate queue for each server, customers enter a common queue. So isang queue lang. And the utilization is lambda over 2 mu or 0.8 less than 1, which implies that a steady state exists. Okay? This is now the steady state. Okay? Now, we need to compute how long are you going to wait in the queue and how many people you can expect in the queue. So kung ang server natin ay pareha silang busy, then you would expect that probability that's both busy because of course hindi naman maglinya yan sila kung walang tao kung walang tao doon na siniserve. So 2.84 at saka average queue is 21.1 minutes. So remember that the average time in the queue kung dalawang separate line ay 48 minutes. Kung isang line lang, 21.1 minutes. Kaya pala, so by pooling the servers, meaning isa lang yung queue, you actually reduce the waiting time for customer by approximately 56%. Imagine, no? 56% ang ma-save mo sa time sa paghihintay kung pooled ang iyong queue instead of a separate queue. Kaya yan, ma-observe niyo dyan sa bangko, no? They give you priority number, so you actually just fall in one queue. And then, kung sino ba yung available na cashier or so itawag na ng teller, kung sino ba yung available, pupunta ka. Hindi ka magpo-form ng line sa harap ng kada isang teller. But kung sino lang yung available, doon ka pupunta. So that actually results to a reduction in the waiting time by 56%. Yeah? Okay. So now we discuss the MM1N. So meron ng same pa rin siya sa MM1, kaya lang merong capacity, finite capacity. So hindi tayo pwede na mag-exceed ng more than a certain number. Okay? So when customers arrive and na-reach na ng queuing system yung capacity, hindi na pwedeng matanggap yung customer na yun. Or hindi na rin, for example, ngayon, meron na tayong mga restriction like sa COVID. Di ba? Ang COVID natin, hindi tayo pwede na mapuno ang ating system ng, let us say, more than 50%. So kung pupunta ka ngayon sa restaurant, and you have to wait to be served, hindi ka natanggapin kung puno na yung unless you are willing to wait. Diba? So sometimes pag puno na, you're not willing to wait na ma-service ka or ma-assignan ka ng table, then that's what we call bulking. Okay? You bulk. So hindi ka natutuloy sa system. So ano bang steady state system? Since meron tayong limit sa system, di tayo pwede makasabi na pi 0 to pi sub infinity, wala na yun. We just limit it to n. Okay? Kung meron tayong n. Yeah? So same pa rin, the utilization, meron siyang steady state if this is less than 1. Kung wala, meaning very erratic yung ating distribution. Wala tayong ma-expect na steady state. Okay? So what's the average number of customers in the system? This is given by this complicated formula, pero it looks complicated, but i-substitute nyo lang yan, makompute nyo na siya. Okay? So what's the special case? If we have lambda is equal to mu, so it means that if you get the ratio, you get 1. Okay? So all states now become equally likely, and system is on average half full. Yes, because kung equal lang ang number of people arriving and the number of people leaving, you would always expect that your system is always half full. Okay? And the little formula is the same. L equals lambda W, lambda, okay, since arrival rate is 0, when there are n in system. Then, that is now the formula. Okay? So, madali lang to kasi mayroong mga formula, di ba? Okay. So, yung derivation na yan, pwede nyo siya mabasa sa libro. O kung nahirapan na kayo, you can always consult to me kung paano siya na-derive mathematically. Okay? So, sa single server, ito naman yung ito naman yung another, no? naging lima na siya. It's because we add the population. Okay? Single server pa rin, exponential pa rin ang poson process pa rin ang arrival, exponential pa rin ang service time, isang server, merong limitation yung system, at saka may finite yung population. Because before, we assume that we have an infinite population. Okay? Although in reality, hindi naman talaga infinite, no? Kahit na sa Pilipinas, sabihin natin 100 million tayo dito, or kasali na yung mga bata dyan. So, kasi mga nasa 60 million talaga yung mga tao. Hindi naman talaga yan siya infinite. It's still finite, but for simplicity, and hindi naman siguro masyado importante na i-consider pa natin, i-restrict pa natin, kaya i-consider natin siya as infinite. Okay? Pero kung the population is really, hindi naman siya masyadong malaki, no? So, kumbaga, may possibility kasi na ang buong population nandun na siya sa system lahat. So, wala na tayo ma-expect na arrival. Parang ganun. Okay? So, or another case is, once lang siya mag-join sa system. Kasi meron kasing cases na kahit na finite yung population, after mo ma-serve, pwede ka pa rin bumalik sa queuing system. Mayroon kasi mga ganyan. Okay? Pero ito is, let us try to model kung talagang merong mas useful na i-model natin ang population natin as finite. Okay? So same thing, exponential pa rin. So 1 over mu ang mean, 1 over lambda ang mean. So ito lang yung illustration, no? So each customer after being served returns population product, having exponential distribution. So babalik lang siya dyan. Pwede naman din dyan pumasok. Okay? So the steady state distribution is you calculate this way. Formula lang, other probabilities are then multiple all, pi 0, or example, an operator can be assigned to service, load, unload, adjust, etc. Several automatic machines in a factory. Running time of each machine before it must be serviced has exponential distribution with mean of 120 minutes. Service time has an exponential distribution with mean 12 minutes. To achieve a desired utilization for the machines, how many machines should be assigned to the operator? So yan yung question. So ito medyo baliktad, no? Sa dati kasi we already have the system, we'll just analyze lang. Pero here we are trying to design the system by making sure that the machine is at least 87.5% ang kanyang utilization. The same din yan, for example, sa mga cashier, di ba? Sa mga grocery, we have to ask themselves, how many cashier ba ang i-hire natin? Or how many tellers ba ang i-open? Parang ganun yan siya. Para ma-achieve natin na hindi naman idle. Pag sinabi natin idle, means walang ginagawa yun as a serve. Diba? Idle yan siya. Pero we want to make sure na at most of the time, di sila idle. Para hindi naman sayang yung binabayad natin. Or in terms of machine, hindi naman sayang yung binili natin mga machine na marami tayong binili pero wala palang gamit. Hindi pala natin siya masyado nagagamit. Okay? Or if not, kulang yung nabili nating machine to service some things or some customers. Parang ganun. So we want to make sure that the desired utilization of the machine that we're going to use is at least 87.5. Medyo okay na yan siya na system. It means that 87.5% of the time they are running and they are not ideal. Okay? So if you have here machine processing jobs, you have here machine being unloaded by operator, right? And the n equals the source population, which is actually around 4. So this can be modeled as MMQ system with finite source population. So machine operator is the server, and the machines are the customers. So 5 per hour and 0.5 per hour. Of course, makikita din natin yan dito sa service time. Okay, so 12 minutes, 5 times 12, 60, correct? And arrival rate natin is 0.5 per hour. Okay. So the steady state distribution, just apply the formula. So for one machine, it means that kung ang lambda natin is 0, it means that walang tao o walang ino-operate. Then the operator will be idle 73% of the time. That's a probability na walang customer. So probability na walang customer ay 73, meaning ideal yung ating machine 73% time. Merong isang customer, 21, merong 2.4, so on and so on. Okay? Now, if there are no machine system, then 3 are busy processing jobs. If one machine is in system, then 2 are busy processing. And the average utilization of the machine will now be 89.3. Okay? We just multiply probability divided by 3. Okay? So that is the finite population. Okay, any question? Okay, I think that's another question. Okay. So maybe you will be encountering this type of problems. So just make sure if our assumption holds, can you assume that the system is finite? Or is the system as a limitation on the number of customers or items that it can accept in the system? Whether the arrival is Poisson, our process is Poisson, or the service time is exponentially distributed. Okay? Okay, so let's now study the case when we have a generic or general distribution for the service time, but we have only one. Okay, so we have M, G1, so arrival is still Poisson, but G is now generic, not necessarily exponential, and we have only one server. But of course, we should have a service time, 1/mu, and a variance. Okay? And the queue capacity is infinite. Okay, so the steady state exists if rho is lambda/mu less than 1. If service rate exceeds the arrival rate, okay, probability that service ideal, probability that service is busy, right? So, but there is no convenient formula in system when J is equal to 0. Greater than 0. Unlike yung mga pinag-compute natin na meron. We will be directly computing from the probabilities. Okay? So ito yung ating L sub Q, which is lambda squared, the variance squared, plus utilization squared over 2, 1 minus rho. So the average number of customers waiting. So after calculating, allow us to compute this. Then we get this formula. Okay? So for the MM1Q, the standard deviation equals the mean service time, and the coefficient of variation equals 1.0. Using this formula for the MG1 queuing system with variance squared, we give results consistent with the formula for MM1. Okay? So yan lang. Ayan, thank you. Meron lang tayong dinagdag dyan actually na variance, no? Sa ating service time. Okay. So the more regular the service time, the smaller the coefficient of variation and the shorter the queue. So kung consistent lang yung mga natin server, no? Mas tayo mas kaunti yung queue. Remember that. Pero kung erratic siya, minsan mabilis, minsan mabagal, then we can expect na medyo mahaba-haba yung queue natin. Yeah? Okay, so that's how you use it, formula. So let's have this. The UI Department of Public Safety has 5 patrol cars. The patrol car breaks down in the request service once every 30 days. The department has 2 mechanics, each of whom takes an average of 3 days to repair a car. Time between breakdowns and repair times have exponential distribution. What is the average number of patrol cars in good condition? The average downtime for a car that needs repair. Okay. Then we have also here a small bank is trying to determine how many tellers to employ. So ito yung, and the cost, merong cost is $100 per day. A teller can serve an average of 60 customers per day, an average of 50 customers per day. You see, arrivals form a pause and process, and service times have exponential fusion. If delay cost per customer is 100 per day, how many tellers should be employed? Okay. So ito yung mga sample natin. Yeah. Okay. So we're going to solve this. I'm going to solve this for you such that makita ninyo kung paano tayo mag-solve ng mga ganitong problem. And this is also for the exam. Okay. Yeah. Marami tayong mga example dito. And then we will try to solve it on a, I'll just send you the solution, but try to attempt to solve these problems. Okay. So I think that's all for now. Thank you for your attention. And we have already covered actually a lot in terms of viewing model. You can also, I will also share this video sa ating Canvas yung mga lectures. Yeah. Okay, thank you and have a nice day.